So I want to talk about why do an NDN tutorial? I mean, why bother? What could you get out of it? And it's not like we expect NDN to take over the universe completely, change the internet, and you better get out in front of it because the world's going to be very different in a couple of weeks, and so get up to speed. It's more that it's we use networking to solve an awful lot of problems in computer science. Almost everything we do today is distributed in some way, and the tools that we use to do networking are basically resting on a TCP/IP foundation, and that foundation was set in the late 1970s, and it was determined a lot by a telephony foundation that was set almost a century earlier. And we're carrying a lot of 2 centuries worth of view of the world into a world that's really completely changed. It was changed first by the internet and then by the web. And there are parts of IP as a tool that don't fit very well today, that don't work very well today. And as computer scientists, we try to expand our tools. So my example is I had this problem at work where I needed to scrape a bunch of information out of a kernel, which is the only place that it was available, and then backhaul it across our internal network to my browser so I could visualize it. And I had a nice JavaScript visualization program sitting on the Linux kernel side. I wrote this homogeneous adapter in JavaScript in Node that's pull the stuff out of the kernel, send it across via WebSocket. It worked. It was big. It took forever to get it debugged, but I was happy. It ran, gave me the picture I wanted. Then I decided it was past time for me to learn Go, so I recoded that whole app in Go. Lo and behold, it was like 5 times smaller, and it worked the first time, and it's worked ever since, and it was way faster. And I remember back in the late 70s reading Tony Hoare's paper on communicating sequential processes, and said, well, that's pretty cool. It's a good idea and a way to break things down. But Go is the first time I've seen Tony's CSP implemented at the language level in a really clean way, really expressive, simple way. And as I was doing this program, I said, that's really, really cool. This works so well, and it's such a nice way of breaking things down. Now, I can't do everything in Go and wouldn't want to. It's not a universal tool. I mean, languages are universal, right? Almost everything we use is Turing complete. So you can solve every problem with them, but a lot of times they don't fit. But after doing this problem in Go with its view of the world, I went back and rewrote my original Node program. Got it down to half the size, and it ran a lot better and faster. It was just using some of the ideas, trying to replicate Go channels, using async await and some other JavaScript contexts. They were just better building blocks, and I was able to do a better job on the problem. So the point of this part of the tutorial is to say NDN's about expanding your mental tool set. It's trying to get you different ways of approaching problems. You can try them in NDN, but you can also use the same ideas, sort of treat NDN as middleware, use it over IP, treat it as a conceptual framework and just say, okay, how do I do the way NDN solves this problem, but in an IP framework? So that's the thrust. A slide saying the same words. So I gotta say, I do that all the time. All the screws in my house are incredibly ugly, and I do this, more often than I want to remember. And I've done things like start a server framework in Perl, and 500,000 lines later say, oh my God, what am I doing? And this is never going to turn into a solution. So I've been there once or twice and regretted it. So you want to recognize, you want to have a variety of tools that you can apply to a problem. So the thrust of this is we've had 40 years of IP. Is it the best tool? I mean, it's a great tool. It's really sophisticated. First thing I did when I got in yesterday was try to figure out where this silly room was. And so UCLA's got a map server. I went to the map server and asked it for a campus map, and it gave me back a nice flash file that was almost useful. It gave me an outline of the building, but no idea of what was inside of it. But this is the internet at its best. I walked into the room, flipped open the lid of my laptop, Googled for the URL, and then clicked on it, and I got a map. This isn't the whole story. So this is what I see, and there's nothing here that isn't doing the job that I want it to do, but there's stuff going on under the hood, and you can sort of see it in the first line of the URL. It's sending to a name, but IP doesn't send to names. IP sends to addresses. So there had to be something that was turning that name into the address of a server. And so underneath the covers, there's another request happening where my laptop is making a DNS request for that server, maps.ucla.edu, and some UCLA DNS server is coming back with its IP address. But wait. So how did my laptop know to talk to that DNS server? In fact, how could it talk to anything? Because I just opened up the cover and it had never been in that building in UCLA before. Well, there's more happening under the covers. One is when I opened the laptop and started the wireless, it was using DHCP to configure itself. So it sent a discover message to yet another server. And it got back a bunch of information, its identity, the IP address of a gateway to use, and the IP address of a DNS server. So at this point, it's got enough network configuration so that it can safely talk. Then it wants to send something to that DNS server. It can look at the address and say, I'm sending somewhere that's not on my local network. This number is different than that number, and therefore I'm going to send it via this gateway. And now it has to say the IP address is a logical construct. It has no physical meaning whatsoever. We're assigning it dynamically. So it has to be bound to a layer 2 link level address. And when I'm using my Wi-Fi, I have to send a packet to that link level address. So I need something that will map from the IP address I'm trying to reach to its link layer address so I can send the packet across the Wi-Fi. And there's a protocol called ARP that will do that. So it's doing an ARP to say who owns this IP address, and it gets back the MAC address. So in order to do that, there's a bunch of machinery that's sitting underneath me. All of it has to work or I can't communicate. Because in order to talk across an IP network, you need the identity of the thing that you want to talk to in the IP world. You need its address. And you need your identity so that you can send and receive packets. You have to, in every packet, you have to put a destination and a source. And the other side's going to flip those around so it can talk back at you. So we need all of this stuff. It has nothing to do with the problem that I was trying to solve, right? I'm trying to get a map, some piece of content to display in my browser. Got a bunch of external dependencies. They all have to be configured. And lastly, these two pieces you can't do within the IP model. So here we're trying to get this information, but remember, to communicate in IP, you've got to have that. You have to have an identity in order to communicate with anything. So how do you bootstrap? How do you get an identity when you don't have one? You have to ask the network for it, but you're in a state where you can't talk to the network. So we hack our routers so that you can issue this DHCP discover packet with a 0 in the address field saying, I don't know who I am, and I'm trying to find that out. You tell me. And by the way, you can't send to an IP address because I don't have one. So remember my MAC address when you got this discover packet, and then you can send the response back to that MAC address. So you have to write what's in this box. All the protocol, its data management, its communication with various backends and authentication, all of that can be written in IP. But the actual bootstrap protocol you can't write in IP because it doesn't meet the IP model of communicating between endpoints. Similarly, you're binding from an IP address to a MAC address. MAC addresses, layer 2 addresses, aren't in the IP model. There's no data about them. So again, you can write most of the protocol that responds to this in IP, but the low-level transaction is written in something else. It's written using an Ethernet broadcast because you don't know who you're going to talk to, so everybody hears it. And generally, the thing that has that IP address replies and says, hi, the IP address is me. So some issues with IP, and there are problems having to do with bootstrapping and starting both at the cold start level, right? Open the lid in a new place. You've got to get yourself configured. You've got to meet the IP endpoint abstraction. And when you start communication to some new party, someone that you haven't talked to before, you have to map their IP logical identity into a real physical identity as far as the link layer is concerned. And those are explicitly not in the IP model. I mean, it just doesn't know how to talk about those things. What is in the IP model? Well, say it was done at a time when the world's communication was telephony. Telephony is all about creating a wire connecting two endpoints. For the phone company, the two endpoints were phones. For us, our endpoints are network interfaces. The way that you identify an endpoint is by its address. In the phone, it was a phone number. For us, it's an IP address, this logical construct. The big advance of IP is it virtualized those endpoints. It said you don't need a physical wire. We'll make one on the fly. We'll make it in some very scalable way. You can compress the state. You can compress the endpoint identities by doing longest match on prefixes. So if you're far away, you don't have to know a lot of the details. You can rebind the addresses. You can get nonce addresses. You could have multiple addresses sitting on an endpoint. Lots of good properties that you get out of turning a hard physical wire or wires going through a patch panel, like when you're doing telephony, into a logical construct that's just enforced at the endpoints. But fundamentally, you're building a wire between those two endpoints, and to make it, to create this abstraction, you need to have names for the two ends. And you can't do anything until you've got those names, because if you don't have those names, you don't have an identity for the wire. So all of this stuff is about building the abstraction that IP needs to communicate. So the problem is 99% of what we do is that top line. We don't care about this. It's confusing. It shows up in our error messages. When things fail, they fail because this got broken or this got broken or this got broken. But that has nothing whatsoever to do with our problem. Our problem's up there on the top ever since we got the web. So You can ask, what is this abstraction buying us? Well, what it buys us is basically turns one server into 4, and it it's causing, I said 99% of the traffic, that's the other 1%. So you look at the communication going over the internet, most of it is about getting the content that people need to do their job, and almost all of the rest is what's necessary to maintain these abstractions. Locally in the form of DNS and configuration traffic, in the long haul in terms of routing traffic, the two things that we need in order to maintain this abstraction. If this abstraction isn't buying us a lot, could we do without it? So that's the starting point for NDN. So how does this look in NDN? In NDN, you can send exactly 2 kinds of packets. One is an interest packet, which is sort of that question mark followed by a name. An interest packet just includes a name, and it's the prefix of the question that you want to ask. It's says, I abbreviated campus / C just because the names are getting too long. But same question as before. I want maps.ucla.edu/campus. I want some piece of content in that collection of content. I can broadcast that name, right? I'm asking the room, anybody have a map of UCLA, right? And I don't need to know your names, right? I know what I want. You can hear what I want. Broadcast is really cool that way. Everything on the wire with me is going to pick up that broadcast. Some box might say, oh yeah, I know how to get to that guy. I exchanged routes with him. So it can forward the question. Say somebody wants the UCLA campus map. Server can come back with now the first chunk of that UCLA campus map. So the semantics of this name, the first part of the answer exactly matches the question. So we're using IP's nice scalable longest match lookup and hierarchical aggregation to reduce the state. The last part uniquely identifies a piece of the content. It says it's this campus map flash file. It's version 42 of the file, and this is block 0 of the whole collection of information. And there will be a bunch more blocks in version 42 because it's a big map. So this is like the web picture. Everything that's on there is something that needs to be on there. If we did the rendezvous via broadcast, if my laptop comes up, it gets carrier off the Wi-Fi, right? It associates with the access point, and now it can send and receive bits. At that point, at the network level, you're done because you can send and receive bits. And there's no abstraction you have to build. At that point, you can broadcast your question and say, give me a campus map. And if there's anything that hears that question that can answer it, that thing can answer. So no infrastructure dependencies other than the basic communication. As soon as you get carrier, you can talk because you don't need identities. You just, the question defines the problem that you're trying to solve. If you're getting stuff that's far away, you're going to need the cooperation of some agent that you can talk to locally in order to find it, to get to it. So there is, like in the IP case, another transaction that can happen under the covers. This is a skeleton. It doesn't really work this way for reasons that you'll find out in the rest of the tutorial. This is asking a question in the NDN configuration namespace saying, are there any routers on this network with me? Is there anyone willing to forward my questions to somebody who might be able to answer them? So that's what that question means. It's sort of the equivalent of a DHCP You're trying to discover agents that will help you on the local wire. Now, remember, fundamental to the communication, the DHCP is a necessary part of IP. It took a long time to come, almost 15 years, and we were manually configuring IP until we got it, which is why IP was run in small labs at universities for about 15 years. But we got DHCP in the early 90s, and after that, everything became self-configuring because nodes could find out about their local environment and their local identity, and that's the bootstrapping that allows them to talk. Fundamental to communication is finding out the resources in the local environment, because you can't teleport your bits across the planet. You can't broadcast to the entire planet. So you need some local help. In IP, the fact that you don't have a wire connecting you to everything on the planet is completely hidden from the endpoints. Their abstraction is if you've got the IP address, you can talk to it. You're connected to it. And this causes all sorts of problems because if there are issues in the forwarding infrastructure, it's invisible to the endpoints. It can't talk to you. You're not aware of it. It's not aware of you. In NDN, it says that's silly. That's an abstraction that works against us, not for us. So when you're talking in NDN, you're always talking to a local agent. That local agent may recursively do what you did. So you send your question to a border router, and it says, well, I can't answer that, but I know a server who can. And so it's going to take your question, send it off to that server, and it's going to remember where the question came from. And again, if I asked a question like, does anybody have the time, right? You might not have the time. You might have to look it up on a web page. Say, when does the eclipse start? You could Google for that. Give me the answer. You don't have to know my name to give the answer, right? You need to know that I'm in the room with you, and you can say it and I can hear it. So you can remember where the question came from. Means you don't need addresses to ask and answer questions. You just need the question and some way to get its answer. And the answer can be something that makes a prefix announcement that server can announce via a local broadcast protocol. If you get a question that starts maps.ucla.edu, give it to me. I can answer most of such questions. And if not, I can send back a failure that says, nope, that doesn't exist. I'm authoritative for this name. So that's how routers learn about things that can answer questions. And this is how nodes learn about routers. And basically, this is that box saying, any question that you can't answer via broadcast, send it to me. I probably know how to get the answer. So it's advertising the root of the namespace. Okay. So with that, this is what NDN packets have in them. So the interest packet, the question has just got a name in it. It's a hierarchically structured name. That's general. It allows longest match lookup. It allows hierarchical aggregation of the routing state so that you get the same kind of scaling that the internet gets. It's got the chunk of data that's associated with that name. And then you need some provenance for the information. I mean, I don't want a random flash file. My browser is going to refuse to execute it, or at least I hope it's going to refuse to execute it. If it's a flash file that's signed by UCLA and I know the trust chain so I can validate that cert, then I'm willing to execute it because I'll guess that they're not trying to hack me. So you need an additional chunk of information, which is the provenance information about that data, or some party that asserts that this name is properly bound to that data, that the two go together, and some certificate, cryptographic identity signed by UCLA is asserting that binding. So that's our packets. So here's a comparison of various communication level architectural artifacts as they're expressed in IP and as they're expressed in NDN. So the biggest one is, what are the entities that are named inside the protocol? What does the protocol know about? What does it care about? In IP, it's communication endpoints, which are interfaces, right? It's the ends of the wire, and it identifies the abstraction it uses to communicate via those endpoints. In NDN, it's these name collections of data. It's you send out a name prefix. The semantics of that is, here's the name of a collection of related data. It may have one element in it, it may have a billion elements in it, but here's the name of some collection. A legitimate response to this question is anything in that collection. The thing that's hearing the question can use its best judgment to return some representative. I mean, this is, you send a web URL that doesn't have the last part of the name. You get back a page that's index.html, right? Some canonical starting page where if you know the site, that will let you query for a starting point to explore the information in that site. The thing that the map server returned for our undecorated query was block 0 of the current version of the flash file, which is almost certainly what you want to start with if you don't ask for an earlier version, or you're not asking to replay, or you're missing block 50. It's a good exemplar of the collection. Is a good starting point if you don't know anything else. So there's a model when you're communicating. Are you talking to a room? Are you talking to an individual? Is it a phone call? Is it one-way or multi-way? Is it a radio broadcast? Or is it an interactive session? There's lots of different communication modalities. IP came out of telephony. The only communication modality in telephony is point-to-point. So that's what it does, is point-to-point conversations. This is really an issue because some of us, unfortunately, like more than 20 years ago, tried to bring multi-point communications, multicast to the internet, and pretty much failed miserably. It's really resistant to trying to do many-to-many communications. It's hostile to the model at pretty much every level. It's hard to configure the communication to have multiple generators and multiple sinks. It's hard to configure the routing, the distribution trees. It's hard to configure the bootstrapping. It's how do you get yourself into the trees that are distributing the information. It just really doesn't want to do it. Dave Clark, the internet architect, at one point while we were doing this said, well, my rule was always, when you're designing a protocol and you want to move it from possible to impossible, you just say multicast. And that was our experience. Awful. NDN, we start saying the world's radios. You know, let's stop pretending that they're wires. They have this wonderful broadcast nature. It means you can ask a question of an entire room with a single packet. Right now, you try to do that with IP, it will send the question to everybody because radios only broadcast, and everybody but the MAC address that its destination will throw it away. So you end up wasting a lot of communication bandwidth to try and put a point-to-point abstraction on top of a broadcast media. And that seems like useless. So let's start, it's broadcast. All the communications going to be many-to-many. If there's data, anybody can grab it. If they have the data, anybody can source it. It can be multiple places. When you're having a conversation with some resource across the internet, you're connected in real time during that conversation. You have to have a continuous packet path from you to the thing that you're talking to and back again. And if that path goes away, then the communication stops. So its abstraction is a wire. It will const it up out of links. It will route around failures, but it has to have a single connected path to communicate, because that's the abstraction that you're communicating over. If there are errors, it will try for a while to reconstitute the path, but at some point it's going to give up and say, no, I can't talk to that thing that we were talking to, so I'm going to reset the connection. The model for NDN is you're getting the information, you're not having a conversation. Anything that's got the information can give it to you. And if there were 3 things that said they have it, is a sync tree rooted at each destination node. So it's a tree but it's a tree where the root is where the data is going. So the defining property of a tree is there's one path between any 2 nodes. So if you're a leaf of that tree, you're a sender, there's exactly one way for you to get to any destination. And the job of routing is to create that tree. Now you're doing it in a completely general graph, right? The internet's at least 2 connected, right? Except for the leaves, except for the house, everything that's a router has an in and an out, at least. Mostly we've got higher degree from tens to hundreds of ins and outs. We use that for redundancy. When something fails, we want to have an alternate path. But you can't routinely use that redundancy. You can't talk multiple ways, even though there almost certainly are many thousands of multiple ways. As you get into the network, the number of possible paths increases exponentially. The goal of IP routing, because you have to maintain this wire abstraction, is to throw away those choices. It says you're going to send on this tree. It's only one legal way. There's only one interface. If a packet comes in, you can look at its destination. There's exactly one interface it can go out. The routing, if that stops working, we'll try and find a new interface. A couple minutes later, your packets will start flowing again. But the main goal of IP routing is to get rid of choice. In NDN, multi-source, multi-destination. Use the multi-destination part. So question comes in, you say, okay, I know 5 ways to get the answer. It's up to me, my goal is to get an answer. It's to maximize the information production, maximize the rate that questions are answered. So I'm going to make a choice among these 5 possible ways to try and answer the question that I got as fast as possible. And it's completely up to the local node, each local node, how it makes that decision. The reason you can leave it up to the local node is packets can't loop. Because when a packet comes in, it has to find a question, otherwise it gets thrown away. We don't allow unsolicited answers. And when the question is answered, it's thrown away. Means that if there's another answer, you asked 2 places, one answered fast, one answered slow. When the slow answer comes in, there's no question for it. It gets tossed. So you can do experiments at each node to say, what's the best way, or what's the cheapest way, or what's the most reliable way in order to answer questions that start with this prefix. You can keep some state on that, tune it over time. You can be constantly testing it so that you've got a hot backup available if something goes wrong. So that flips the way that you think about routing. In here, routing is about building trees, so it's pruning off alternative branches. In NDN, it's all about answering questions. If routing can say, oh, there's a new way to get an answer to that question. It wants to tell you as soon as possible. It wants to give you more choices, because that's going to make the network faster and more reliable. So very different goal. You're seeing much more of the topology. You're trying to probably emphasize the diversity in the topology, because we're using spatial diversity to try and get us more reliability. So the summation, it's reason for looking at NDN is it gives you some new ways to think about transport. Instead of having a conversation progress through a serial stream of bytes, instead you think of there's a set of information, and any party holds some subset, possibly none of it, possibly most of it, doesn't matter. And their goal is to have all of it. Every piece of the information has a name, has its own unique name. Right, it's part of a collection, but it's block 1, block 2, block 3. And you can send out a summary of your collection and say, this is, I want the collection that's a campus SWF file. And here is a checksum that's the checksum of all the pieces that I have. And somebody else who has, so I can say a question, here's my checksum for this collection of data. Do you have anything different? Does anybody have anything different? And somebody hears it and they have that collection, they say, oh, I have a different checksum. So now either I have something the other guy doesn't, or he has something that I don't, or we both have something that the other doesn't. No matter what, we should talk. We should synchronize our collections because our goal is to both know everything about this collection. Again, that's really robust. Everybody can be moving around. The connectivity can be constantly changing. The state that you've got is 100% the data you have. You don't remember who you talked to, where you got the pieces. You just know that you've got the pieces. And the things that you have identify your state, the sub-collection of the collection that you currently hold. And you can do a protocol with anybody else. You can do a simple question that says, here's what I got, and you're asking, do you have anything different? And then you can run a protocol at the NDN level that figures out what the differences are and exchange them. We've recently found, not in the NDN project, work at UC San Diego and UC Irvine on this set reconciliation problem, that you can resolve the differences between two sets with a communication that's linear in the differences. You don't need to talk about everything in your set. You only need to talk about what you don't have. And that's exactly what point-to-point TCP does. Its communication is linear in the differences. The two ends are, one party has all of the conversation, the other party has none of it. And you exchange sequence numbers until both parties have all of the conversation. But you can do a protocol as efficient as that in a much more general model, which is really nice if you have things moving around, if your life is spread over 100 different devices and you would like them to all have your mail and all have your contacts and all have consistent browser caches or what you've looked at, and you don't want to rely on the cloud. You'd really like your life to be self-contained rather than all on servers in Google. Well, set reconciliation between your phones and your laptops and your pads and your desktop. That's a really nice transport model because it does that abstraction. It lets you spread your life over multiple things in a pretty painless way. Routing, because you don't have to enforce spanning trees on your topology, you can use the entire graph, and you don't have to restrict your view to a graph. You can use what's called geographic routing, where rather than distribute paths and have to enumerate every way through the wide world, you can just distribute coordinates and say, I'm at this point in planet Earth, you know where you are, figure out how to get to me, right? You've got a road map of the local vicinity, pick a road that heads towards me, and then when you get closer, pick a new road that finds it. So that's the way that we tend to navigate in the real world. That's not the way we can do it on our network because we have to enforce this tree property, but it is something that you can do in NDN. I think the tutorial or a paper session is going to cover some of the NDN prototypes on this in hyperbolic routing. It's really exciting work because it's got wonderful scaling properties. And lastly, you can really do security in NDN, right? Because you can do it on the content. You can do really robust models, and the attack surface is tiny because the data gets secured at the point of origin, at the point that it's created. almost any of these things, this you can do in IP, just steal the NDN ideas. This is harder to do in IP because it's got this restriction on its distribution topology, but you can approximate it via an overlay. This you can definitely do in IP. This is just give up on the idea of perimeter security because it never has worked and never will. So these are all ideas that you could use the way NDN did this, and it's 10 years worth of NSF-funded research and existing implementation and testbed. There's a fair amount of maturity in the software base. So that gives you some worked examples. That could be a starting point if you have a problem like this that you need to solve. And so I'll leave you with this, that it's sometimes you got the wrong tool, but it's often easy to get a different one.
I'll ask a question. At the very beginning, you mentioned about the fact that you've been playing with the Go programming, and you can see the commonalities in terms of methodology of thinking, but you didn't elaborate on that. I'm just curious.
Well, I tried actually. So, sort of, so, yeah, just personally, I'm still excited about writing this complicated thing in JavaScript and Node, and then redoing it in Go and going, God, that was so easy. I mean, I thought the problem was intrinsically hard, but it wasn't. I was just using the wrong building blocks. So all of these things are hard problems in the IP architecture.
How
right?
Are they reflected in the Go programming?
So nothing about Go programming is purely analogy, right? It had a set of abstractions embodied in the language that really worked well for that problem and a half a dozen similar problems that I've tried it on. It's extremely lightweight processes, the channels model for communication and the synchronization across channels rather than synchronizing via shared memory and mutual exclusion primitives. All these things were clear from Tony Hoare's paper and his subsequent book, and a lot of development that's been done on CSP, since the paper was 78, the book was late 80s. There's a whole design methodology that's built around it. None of that was real to me because it wasn't sort of embedded in an implementation framework that I would use to solve problems. There was a bunch of math, a bunch of theory, a bunch of new language constructs and tools to learn, and it felt powerful but disconnected and remote. Go was easy, it's complete, it's got a fabulous library. It's got Tony's model as just this first-class entity that's really seamlessly put into the language. It's, you can express operations naturally in a line or two that even in the current CSP frameworks take a page of code, right? So it's so it was the very clean, very natural implementation that suddenly turned this thing from an academically very interesting but very remote from day to day to this is a tool I want to use every day. And my feeling is you could use NDN. It's a really good building block, and it does some things that are hard in IP very easily. It's still got rough edges because it's a research effort. It doesn't have a wide deployment. We're getting pieces like It took 20 years for the internet to get DHCP. We managed to do it in just 6. So we've got a lot of the auto configuration, but you still have to build a bridge from here's the problem I want to solve, here are the NDN libraries and infrastructure, how do I connect those together? And I think in some of the tutorials this afternoon, Bashwan and Jeff are going to go through exactly how you build that bridge for things like Internet of Things applications, which are a really good match to NDN. But I mean, it's not about go code in Go. It's about think about NDN.
Thank you. You just made the analogy about the usefulness and the importance of the tools.
You're thinking on set reconciliation. You mentioned matching up the differences between sets. I assume that's something that happens more at the application layer. Some messages going over NDN talking about what do you have, what don't I have. And if that's the way that I discover content in the network, why is it necessary to do longest prefix match at the network layer? If I find names of content through a protocol that's at the application layer.
So two parts of the answer. One is NDN is not very layerist, and that's personal philosophy, but it's shared in other parties. Dave Clark and I, a long time back, everything I did is 20 years back. 20 years back, we wrote a paper on application layer framing, which is basically what you should put in the network is just muxing and demuxing and packets. Everything else should go in the application. And the fact that it wasn't in the application is more an accident of history than an architectural choice. It was actually intended to be in the application. And there were some issues with Multics that caused Multics, which was the initial DARPA-funded implementation, that caused it to get pushed into the kernel. And the reason is when a packet came off the wire, you had to deliver it to something. But most of the applications in Multics spent their entire life swapped out because there wasn't enough memory on that time-sharing system because memory was fabulously expensive. And because of that, you wanted the receiver for the packets to be sitting somewhere that was always running. And because the communication lines cost way more than the computers, you wanted to keep the communication lines busy. They were leased lines, and if you weren't using them, it was money going up in smoke. So you wanted to look at the packets coming in and say, is this okay? Am I missing something? Was it corrupted? So that caused a lot of protocol processing to migrate from the app into the kernel. Wasn't architectural. NDN, it's following everything's in the app. It has to be, because if you're generating data, the last step is you have to sign it. You have to sign a complete unit. And after that, it's immutable. It's not going to change. So any of the semantics of the data, any of the semantics of the name, anything that gives a meaning to this data in a larger context, like is it a sync collection? Is it something describing the network infrastructure? Is it a block of a file and I want to get all of the blocks? All of those semantics, they've got to live in the application layer. They can be in a library for the application layer because there aren't all that many abstractions. And so you can make a sync library, and you can make a file transfer library, and you can make a bootstrap network configuration library. So no user has to implement it, but it's living in a library in the application because some of us believe that's the one true way that undoes this accident of history that constrained IP. And with all that rambling, I forgot the second half of the question, which is, why don't you get your routes via sync? Well,
Not a question was,
you do.
Do the routers have to do longest prefix match if they're just exchanging packets for the application layer, which is the one that's discovering the name?
So if you had, so there's another alternative for naming in information-centric networking, which is called self-certifying names, where the name of a data item is simply a cryptographic checksum of that data item. And so if you've got the name, you can ask for, give me the item that matches this checksum, and when you get it, you can check that you got the item that you asked for because you run the crypto algorithm, make sure it gets the same sum. Two problems with that. One is the amount of state scales like the amount of content. And so there's a big incentive to make all your content objects really, really huge because otherwise there's a name explosion. There's still a name explosion because we're producing exabytes worth of content even when you do things that are really, really huge. There's a more fundamental architectural problem, which is to ask for a piece of content, you have to know its checksum. The only way you could know its checksum is if it existed, because you can't checksum something that doesn't exist. That means a name can't be something like a Google search query, right? Because you don't know what the answer is when you ask the question. You want to say, look for this. I can't give you a checksum for that. In fact, the only questions that you can possibly ask in a self-certifying name system are ones for which you already know the answer. And that's kind of a limited system. It's really good for static content distribution, but we do a lot more with the internet than static content distribution. So massive scaling issues if you go that direction, because names explode and there's no way to control the explosion. And the architectural limitations, the system's expressibility is really, really limited compared to NDN. In NDN, you can ask pretty much any question, including ones where you don't know the answer.